Welcome to module 39 of database management systems. We have been discussing about query processing and optimization. In the last module, we talked about the basic issues of query processing, what is an overview, and the measures of query cost that would be used in terms of disk seek time and disk access time, the read write time. And we agreed, we assumed that we will ignore the CPU and other time for the time being. And then we took a look into how the certain SQL queries like the selection, the sorting, which is required for other operations, different join operations and other aggregation and those kind of operations can be processed in a structured way. In view of this, in this module, we would like to understand the basic issues of optimizing queries. So, that the same query, as we have seen little bit, can be performed, executed in multiple ways, and we would like to choose the one which is the least cost, possibly estimated cost should be the least. So, we would need to understand two aspects. One is, given a query, how do I generate alternate queries, that is in terms of the relational expression, how a particular expression can be transformed into equivalent expressions, and then we choose from these equivalence expressions for optimization. So, these are the two topics to discuss. So, to introduce on the query optimization, let us take a simple example. So, I am referring to the university database that we have discussed earlier. It has three relations as listed above, and using that we want to perform the query where we join instructor, teachers and course, these three relations, and do a selection on that based on department name. So, this will give us naturally the instructors who are in teaching some course in the instructor is in music department and is teaching some course there, and we want the name and title of these. So, we want the name of the instructor and the title of the course that the person is teaching. So, if we write the query in equivalent relational form, this is what we will get to see, and this is this basically is the first join happening here, then the next join happening, next the selection, and finally, the projection happening here, which will give us the result of this query. Now, what we observe is, it is possible that if you look at carefully, the department name should be music. So, if we look into these relations, then we can easily figure out that instructor has the department name attribute. So, in this, after this join, if a tuple has to qualify through this selection, then the instructor in the instructor relation, the department name of that join tuple must be music, otherwise it will not get selected. So, what if instead of doing the join and then doing the selection as we are doing here, if we first do a selection on the instructor relation itself and then join it with the join of teachers and courses and finally do the projection, we should actually get the same result. So, these are what is a simple example of what are equivalent relational expressions that we can make use of in terms of our query processing. So, given that this is another example we were showing. So, here the query is to find the teacher and instructor and the course name, for where the instructor is from department of music and the course he taught is in the year 2009. So, we want these, and corresponding to the equivalent SQL, if we write the relational expression, then in relational algebra this is what it looks like. So, what we can eventually observe from this, that again as we observed last time, department name is on instructor. So, if we are doing a final selection based on department name is equal to music, then it is possible that I can first filter the instructor relation with the department name being music, that should not affect the result. At the same time, the other select condition we have is year is 2000, which happens only in the teachers relation. So, instead of actually filtering it after the join, I can filter the teachers relation with year being 2009 and then use these two in terms of the join, and finally join that with the course and finally do the projection. So, here what we show that along with this tree, the parts tree of the query in relational algebra, we are also trying to put some annotations to say how this particular query will be processed. So, if we want to find out the tuples where the year is 2009 and there is no specific index on that or anything. So, for doing this selection, as we have seen earlier, the best way would be to use a linear scan. Whereas, if I am trying to do a selection with department name is equal to is music, there will be could be an index 1, the secondary index based on the department name. So, I will be able to use that index to find this. So, these when we are doing this putting in that here we will use this index, here we will use linear scan. These are what is called annotations, which tell the query processing engine that how the query should actually be executed. Then this will be pipelined in the sense that this will be put one after the other. Actually, these two can happen in parallel, and then we will use a merge join to join these two. Then this merged this join result would be joined with course based on now the course is already indexed in course ID, and this joined relation of instructor and teachers will have ID and course ID on which they will have index. So, we can use a hash join on that. We did not discuss about merge join, hash join as processing steps in detail, but right now just assume that these are different ways of doing join which can make things efficient, and these are the annotations which are generated in the process. And such a query tree, such a query parse tree with the annotation is called an execution plan. So, that or the evaluation plan, which the query processing engine would be able to use to actually execute and find the results. So, this is the basic approach. So, for optimization, what do we need to do? We need to find out that particular evaluation plan, that particular order of evaluation and the use of algorithms, the use of indexes, which will make the query possibly most efficient, and that cost difference could be really huge in a real database. It could vary between seconds in one way of doing the query or in terms of number of days if we do it in a non-optimal way, in a non-optimized way. So, typical steps in this kind of query based optimization would be to first generate the candidates. First generate the candidates, that is generate the equivalent expressions, that is given a query. I have one relational expression and we would like to generate equivalent expression using a set of equivalence rules. We will see what these equivalence rules are. So, that these equivalent queries expressions any one of them can be actually executed, and we then annotate them to with the resultant expression we annotate to get different query plans, evaluation plans, and then we put the cost estimates based on the cost structure that say we had used in the other in the earlier module, and from these alternate evaluation plans we will choose the one that will have the least estimated cost. So, the cost can be based on, as we had seen earlier, it could be based on number of tuples, number of distinct values, frequently used attributes and so on, and we will use statistics for also intermediate results, that if there are intermediate results to be stored, we will make estimates of what would be the size of that result, because it needs to fit into memory for optimal execution. The cost formula for different algorithms will also be used through statistics. So, based on all these estimation which will have an estimated cost, and based on that we will choose the particular evaluation plan which looks to be the best. and that is the crux of the query optimization strategy. So, as we have seen, the first step is to be able to generate alternate expressions, equivalent expressions through transformations. So, we look through the relational algebra operators again and check what is meant by equivalence of two relational expressions. So, two relational expressions are equivalent if they generate the same set of tuples for any instance of the database. It is not enough to just show that for one instance it gives the same result. So, two expressions are equivalent for if I take any legal instance of the database, then it must be equivalent. And in this process we can note that the order of tuples are irrelevant, that we have told repeatedly, and also we would make sure that the results are same provided the database provided the relations satisfy all the integrity constraints. If they violate integrity constraints, then it is a problem of the user, then the database really does not care if the two expressions will give equivalent or equal results. We also note that in SQL input output could be multi-sets. So, the same thing has to be satisfied in terms of multi-sets. So, based on this we define an equivalence a set of equivalence rule that say that two expressions are equivalent. So, you can use that rule to transform one expression by the other and vice versa. So, let us take a look into this expression. So, most of these expressions are relatively easy to understand. They can be formally proved using the corresponding set theoretic condition of the relational expressions. So, for every relational expression we had a set theoretic condition that we had studied. So, using those you can prove that. We will not do the proof of these equivalence relations here, but you should be able to do that very easily. So, if we have a conjunctive selection of a relation based on two conditions theta 1 and theta 2, then we should be able to apply the selection first based on theta 2 and then based on theta 1, or actually vice versa, because conjunction is commutative. So, the selection operation is also commutative. So, this gives us two transformation rules, and we might want to use any. So, these all will give equivalent form. So, applying these two rules we get three relational expressions which are all equivalent. This and this are all equivalent. But if you actually think in terms of processing the query and the cost involved, you will be able to figure out that naturally the cost of doing this may be relatively more involved, because you have the relation and then on the whole relation you are applying the conditions. But here if you do, for example, if you first do say first apply theta 2, certainly by that selection the relation would become much smaller. So, applying theta 1 on that would be easier, or vice versa, depending on whichever is a smaller set. There could be other, for example, if you have a sequence of projections, then naturally in that sequence the last projection that you have done is what is retained. So, if we have a sequence of projections, that is simply doing the last projection, all other projections can actually be ignored. The selection can be combined with Cartesian product and theta join also, that is taking a Cartesian product and then doing a selection is equivalent to doing a theta join. This of course is almost the definition, and if I have a join by theta 2 and then do a selection with theta 1, it is equivalent to doing a theta join with theta 1 conjunction theta 2. So, these are all equivalent forms. So, these are equivalent in the sense that left hand side and right hand side are interchangeable. So, it does not mean that the left hand side implies the right hand side or vice versa. It means that either of them implies the other, they are really equivalent in that sense. Then theta join operation are natural join operations are commutative. We can interchange the relations. So, this might impact, for example, you have seen the algorithms of nested join and block nested join algorithms. Obviously, depending on the size of the relations, the cost of doing theta 1 E 1 theta join E 2 or E 1 natural join E 2 and E 2 natural join E 1 may be different, and we would choose the one which has a lesser cost. Next set of transformation rules tell us that the join operation is associative, which is obvious. Theta joins are associative in this specific manner also. That is, if I do a theta join with condition theta 1 and then do a theta join with condition theta 2 and theta 3, then we may be able to take out the condition theta 3 outside, provided theta 2, the condition theta 2 uses only the attributes of theta E 1 and E 2. So, it should be possible to do that. Look here that on the left hand side, that restriction is not there on the condition theta 2. It could also use attributes of E 1, but if it does not, then it is possible to simplify it in this manner, and these are the equivalent rules that we have. So, often we will draw the rules in this form. So, just to explain you one. So, this shows the associativity of join. So, here what you are saying is, first you do E 1 E 2 and with the result you join E 3. Here you are saying first you do E 2 E 3 and then you join with E 1. So, this is basically associativity. This basically is commutativity of theta join. So, we will often draw them in such forms of Peirce trees and show the equivalence. That becomes easy to understand. For example, in this case you are doing a join and then doing the selection, and here you are doing a select early, you are doing a select early on this relation E 1. Of course, you will be able to do this provided theta contains only attributes from E 1. If theta contains attributes from both E 1 and E 2, this transformation will not be applicable, this transformation will not be possible. So, these are some more of the transformation rules. The selection operation distributes over theta join operation. So, I can you can see here that there is a theta join and then I am doing a selection. So, I can first do the selection and then do the theta join. Of course, for the selection it must involve only the attributes of E 1, otherwise this will not be valid. And similarly, another distribution rule is shown here, where you are doing a selection on conjunction on theta 1 theta 2 on a theta join by theta, then you should be able to actually distribute based on the condition theta 1 and theta 2 if theta 1 involves only the attributes of E 1 and theta 2 involves only the attributes of E 2. These are pretty straightforward rules if you think about the corresponding set theoretic reason. So, the other rules will be in terms of projection. So, you can have, if you have union projection like this, then you would be able to break it down over two separate projections and their theta join. And in case you have a theta join of E 1 E 2 based on theta, and if L 1 and L 2 are the attributes of these two relations. So, L 3 be the attributes of E 1 that are involved in the join condition theta, and L 4 are what are. So, you have the join condition theta. So, what you are saying that the attributes L 3 of E 1 are involved here and attributes L 4 of E 2 are involved here, but they are not so in terms of L 1 union L 2. So, then this kind of I should be able to distribute the projection in steps and make the results smaller. So, this is another possible transformation that now, finally, the set theoretic operations have their normal set rules. So, union and intersection are commutative. Naturally, set difference is not commutative. Union, intersection are associative as well. The selection operation distributes over union, intersection and set difference, and the projection also distributes over union. So, you can see the exceptions here, you can reason that out. So, we have in short we have presented a set of different transformation rules by which you can make equivalent expressions, and between two equivalent expressions or more equivalent expressions, our objective will always be to choose the one whose evaluation plan will have a lesser cost. So, as an exercise I have left that you can create equivalence rules that involve group by or aggregation operations or different kinds of outer join, left outer join, right outer join and so on. So, please work those out. Let us move on to a couple of examples. So, here is a query, here are the relations from the university database. Here is a query, find the names of all instructors in the music department along with the titles of the course they teach. So, a while ago we saw this. So, this is what the query is in the relational algebra form. And if you use the transformation rule of select early, the rule 7a, whose transformation I have just shown here, then you should be able to, here what you are doing is you are first doing a join of teachers and the projection of course, and then joining instructor with that, and finally doing the selection. But you would be able to do this select early, because it involves the attribute department name, which is the attribute of instructor alone here. So, you should be able to first do this selection. Mind you, here courses also show that there is an attribute department name, but actually the courses is being used after projection. So, after projection in the projected relation there is no department name. So, department name is involved only the instructor. So, I can take this do early, I can do this selection early and take this out and then do the final join operation. So, in that process possibly this will reduce the size of the relation to be joined significantly, because you do not naturally expect to be to have too many instructors in the music department. So, the instructor relation after the selection would become much smaller. So, this is one example. This is another example query we are taking. Find the names of all instructors in the music department who have taught a course in 2009 along with the titles of the course they taught. So, here is the corresponding relational query, which you can convince yourself is indeed the same, and then we can transform using the rule 6a, which I have shown here, which is basically the associativity of join, because there are two join relations and we are using the associativity of join to first join the, here the second and third relations are joined first and then the first relation is joined with that. Here we are using associativity of joining the first and second and then using the third. Now, if you join first and second, and then it is possible that the department name actually the department name is in instructor, and the other condition is year, which is in the teachers. So, this department name is in the instruction, year is in the teachers. So, I should be able to do select early, I should be able to select on the instructor based only on the department name being music, and also select early on the teachers by using year as 2009 and then do the adjoin. So, naturally each one of these will become much smaller corresponding to the whole instructor or teachers relation. Therefore, their join will also be smaller. So, which means eventually this part of the query will become much smaller in size in the result, and the consequent second join would be much smaller to perform. So, this will naturally give a, whereas if we had done all of these join earlier, we would have used the whole of the teachers and the instructor relations, and that would have been quite a lot of tuples would have been there. So, these are different examples. So, this is the same example being shown in terms of the tree parts tree structure. So, you can convince yourself by using the transformation rules that they are actually equivalent, and then certainly they give you a significant advantage. And this is an example which show that you can push the projection. So, here is what you wanted to do, and while we compute this, we will get a relation of this form, and we can push, we can use these rules, rule 8a and 8b. This is rule 8a, this is rule 8b. By this we can push the projections inside and make the relations smaller, because now if you push the projection, then you are actually cutting down on the number of columns. So, your relation becomes smaller. That will make the with the projection, this will reduce, and when you project also there will be duplicates which will get removed. So, in every way your relation becomes smaller in size, and your subsequent join operations would be more efficient. You can also these are examples where you can take care of the fact that you can reorder joining to get better result. For example, if I have to do join 3 relations like this, I could do either this first or this first. Now, if I do this first, then this is a temporary relation which I will need to maintain in memory and then join with R 1. If I do this first, then this will be a temporary relation and then I will join it with R 3. So, if this is large enough, then compared to this, then I will be better off by doing this, and will be able to have a more optimized execution of the query. So, here is an example of that, again 2 joins. So, what we are trying to show is when we are having this, instead of we are actually trying to compute this join first, because we expect that this set to be much smaller. If this set is much smaller, then naturally this join would be much smaller and it is more likely to fit into the memory than if we had just done teachers and course IDs, which I expected to be large relations. So, basically therefore, the strategy turns out that given a query, you will have to generate whole lot of equivalent expressions. So, the number of equivalent expressions could be really large. So, you will have to systematically generate all these alternate equivalent expressions and apply by applying these transformation rules that we have just seen, and we will have to continue till no new expression can be generated, and then we have to evaluate each one of them based on their evaluation plan. So, this could be very expensive because the number of alternates could be really large. So, the optimized plan generation is also based on the transformation rules, and we may have different special case approaches to take care of the common optimization plans that we might have. Now, one way to do that is for example, if we are looking at say the join of 2 relations E 1 and E 2 here, then obviously, if we do certain transformations with this join, that does not change the way E 1 and E 2 are actually evaluated. So, if that be the case, then in terms of generating the alternate, we do not really need to keep or evaluate all of the expressions, the whole of the expression in every alternate. We could actually do something like we could actually do something like we could have a join, and then instead of really replicating the whole of the evaluation of E 1 and evaluation of E 2, we can simply make pointers to the same subtrees, which are called basically sub expression optimization. If you have studied the expression optimization in compiler at any point of time, you will understand this very well, because it is the same strategy which is used here. So, if you can detect duplicate sub expressions, then you can have only one copy, and you can make the things more efficient to run. So, the general strategy for doing this is dynamic programming. We would not be able to cover that in the current course, but just know that all these explosion of generating alternate and choosing the best one is usually handled in terms of dynamic programming, which is a strategy to make sure that if we have solved a sub problem earlier, then I do not need to solve that sub problem again. We can just reuse that same earlier result and go ahead with that. So, by this way we can common sub expressions, we may only find the plan for a best plan for a common sub expression only once and then use it subsequently again. So, in this module covered starting from the notions of query processing in the earlier module, we have discussed the basic issues of optimizing queries, and we have shown that using a set of simple transformational rules, you can convert a relational expression into a number of equivalent relational expressions, and then you can evaluate them based on the estimated cost that the model that you are using and choose the best one, and dynamic programming is usually a good way of doing that. So, Through the previous module and this one, we have taken a very elementary look, I should say, but this will give you some idea of how actually an SQL query is transformed into relational algebra, parsed and translated into relational algebra, and how equivalent expressions for that relational algebra expression is generated and evaluated, and finally, an evaluation plan is made where specific choice is made for the different algorithms for doing different operations, and that final plan which has the best cost is passed on to the query processing engine, the query evaluation engine, and that then goes forward and does the B tree and disk operations in according to the plan and produces the best result in possibly the shortest possible time period.